Okay, here we are with Lesson 21, and it's the time-dependent perturbation theory. I'm going to focus on an application, since I want to try to consider applications more frequently. So I've tailored this whole conversation around the issue of what happens when an electromagnetic wave interacts with an atom. Now, many of the interesting situations occur when the frequency of the electromagnetic wave matches an energy difference between two particular states. And in that case, you can pretty much ignore all the other states because their effect on the situation is negligible, and just focus on the two states that are involved in the interaction with the electromagnetic wave. And I'm only going to consider today a monochromatic or a exact single frequency electromagnetic wave. And next time we'll see what happens if the electromagnetic field has more frequencies in it. But today we'll just focus on a single frequency. So let's get started. The idea is to imagine you have an unperturbed system, an atom just sitting there, and then a time-dependent perturbation comes along and affects it in some way. The notion is that we can describe the atomic quantum state as a superposition of a little bit of state A and a little bit of state B. And we're going to further assume that we start out in state A and we make a transition to state B. Now normally, if there's no perturbation, the Fourier coefficients, the amplitude to be in state A and the amplitude to be in state B, are constant. They don't change in time. But what we're going to do is to incorporate, we're going to solve the Schrödinger equation by permitting the CA and CB now to become functions of time that evolve according to the effect of the perturbation. So that's the idea. So here's the Schrödinger equation. We plug in the Schrödinger equation as a little bit of the original unperturbed Hamiltonian plus the perturbation. And when you take out the terms that cancel, of course, you know that the unperturbed Hamiltonian acting on state A just gives you the energy EA and so on. And I'm going to define omega A to be EA over h bar and omega B to be EB over h bar in the normal way. Anyway, when the smoke clears, you end up with this expression. So notice that there are derivatives of the coefficients in there. They come from the derivative of the wave function, which of course is got products of these coefficients and e to the minus I omega t and so on. What I want to do now is to hit with A or B from the left, and we get these expressions. I'm using the shorthand H prime AA, excuse me, is the matrix element between state A and state A of the perturbation and so on. We get these two expressions, and they are expressions for the time derivatives of CA and CB in terms of the current values of CA and CB and the matrix elements of the perturbation. So notice if the perturbation is 0, CA dot and CB dot would be 0, which just means they're constant, which would be the case if there's no perturbation. So I also want to focus on a case that's generally true, a situation that's generally true, and that is that the diagonal matrix elements are 0. So let's assume that those guys are 0. There's a nice problem in Griffiths that encourages you to investigate what happens if they're not 0, and the answer is not very much interesting happens. You just add or subtract a constant to the energy, essentially, but it doesn't have any real effect on transitions, which is what we're interested in today. So let's just focus on the case where their diagonal elements are 0, and that simplifies the equation somewhat because it gets rid of those CA terms in the CA dot equation and the CB term in the CB dot equation, and you just get that CA dot is proportional to CB and the matrix element between the AB state in the perturbation, and CB dot is proportional to CA and the matrix element between the B and A states of the perturbation. So notice what that says is CB dot, the perturbation basically connects CB with CA. If CA is not 0, then it gives CB dot a value. And if CB is not 0, it gives CA dot a value. So the amplitude to be in state B is going to change if there's a large amplitude to be in state A and there's a connecting matrix element through the perturbation. So here's the idea. Let's say we started out in state A at t equals 0. How do we express that? Well, you just say CA is equal to 1 and CB is equal to 0 at t equals 0. So that means the system is definitely in state A. And let's further assume that H prime is in some sense weak. So that means that the rate of change of B is going to be slow, say compared to omega naught or omega B and omega A. Oh, by the way, I snuck in here a definition. I'm defining omega naught to be the difference in frequency between state B and state A. I don't know if you caught that. I should have said something back in those equations, but if you look at the top of the screen, you'll see that I've substituted omega naught for the difference, omega B minus omega A. So what I can do then, if H prime is weak and CB is 0, then I can forget about CA dot. It's not significant because CB is 0 and H prime is weak. But CB dot, because CA is 1, CB dot is not going to be negligible. And so I can simply integrate that equation, substituting for CA. I'll just put in 1. It's a constant value. And I get an integral that I can evaluate. And I'm interested in particular in electromagnetic oscillation. So electromagnetic fields. But we're talking about optical fields where the wavelength is many, many times the size of an atom. So I can just assume that I can calculate the matrix element H prime AB and H prime BA. It's going to turn out, we'll talk about this a little more next time, but as we've seen before when we talked about the effect of a constant field on various things, harmonic oscillators and square wells and so on, it's proportional to the matrix element of the position. And that's simply because the wavelength is so long that the field near the atom is essentially a constant in space, but variable in time. So it's just a constant field multiplied by a cosine. That's the idea. And I'll go ahead and put that perturbation in, and you can see that what we get is the integral of a cosine. That's an easy integral to do. We break the cosine into e to the plus I omega t and e to the minus I omega t, and we simply crank it out. Now, it's not a very enlightening result, unfortunately, so I'm going to make what people often make in this business. I'm going to say, let's imagine that omega is very nearly equal to omega naught. So that means if you look at these two expressions, the omega plus omega naught is going to be much, much, much greater than omega naught minus omega, or omega minus omega naught. And for that reason, that first term in this expression is so small, I can basically neglect it compared to the second. That's the idea. This is the so-called rotating wave approximation. And if I make that approximation, this expression simplifies. I can kind of factor some things out. I can convert that numerator into a sine function by factoring out an e to the I omega naught minus omega t over 2. And we get the following somewhat simplified result. And I can use that to compute the probability. Now, the first thing you'll notice about the probability is it's not a constant in time. In fact, it oscillates in time. So, and it oscillates with the frequency that goes like the difference between the electromagnetic wave frequency and the difference in frequency between the two states in question. So the probability ends up looking something like this. Of course, it has a maximum value that depends on the detuning. Detuning is a measure of how far the electromagnetic wave frequency is from the resonant frequency, omega B minus omega A. And of course it's proportional to the matrix element of the perturbation, VAB, the amplitude of that matrix element between the two states. That's the idea. And also the period of that oscillation depends on the detuning as well. So if the detuning goes to 0, the period becomes very large. So you can think of it's almost like beats. There's almost a beat between the electromagnetic field frequency and the resonant frequency. Also notice that the probability blows up, the maximum probability blows up if the detuning goes to 0. This is a consequence of the fact that we only did the one term in the perturbation series. This is the first non-zero term in the perturbation series, which generally you'd have to do an infinite number of them to get the exact answer. So our result is only valid as long as the probability remains small. So that means we either have to look at very short times if omega naught is very close to omega, or we have to look at very large detunings, stuff like that. In a little bit we'll do the exact analysis, and we'll see that it comes out sort of similar, but it has no such restriction. So we'll see exactly what happens even if the detuning goes to 0. Let's look at the probability as a function of frequency at a given time. So at a given time, if you look at the probability as a function of omega, you'll notice it looks something like this. It looks like a sinc function, sinc squared actually. It's sine x over x, or sine something times omega divided by omega squared. And it has a definite peak. That peak occurs at 0 detuning, and the width of the peak is quite interesting. It depends on time. So the longer you run the field, the narrower this peak becomes. Now this goes back to the time-energy uncertainty relationship. Remember that the longer you run, the longer an experiment takes, the more precise the energy has to be. This is basically what this is saying. If you run the field for many cycles, then in order to get any appreciable probability of being in the excited state, then the detuning has to be very small. If the detuning is very large, you end up outside of this range, omega naught plus or minus 2 pi over t, and you don't get any appreciable probability. So that's a fascinating result, and we'll probably talk about that more when we talk about what happens when you introduce collisions and what happens when you have more states that the thing can go to, for example, in an ionization or something like that. But let's go back and start over again. You know, I made that rotating wave approximation where we said omega naught plus omega is much greater than omega naught minus omega. I made it after we had already done the first term in the perturbation series, and I had done the integral solution for CB dot, or for CB. Let's see what happens if we put it in at the beginning. In other words, we make the rotating wave approximation now, before we do any integrals or anything. We say that, well, let's let HAB prime. Essentially what I'm going to do is to take out instead of putting in cosine, which is e to the I omega t plus e to the minus I omega t, I'll get rid of the minus I omega part and only leave in the plus I omega part. This has the same effect as that rotating wave approximation. And but it turns out, if you do it at the beginning, you can actually solve this thing exactly. So let's do it. We'll make that substitution, put in the perturbation, and I'll actually combine that in the exponential as a single exponential. What we're going to do is to differentiate the right-hand equation and substitute that into the left-hand equation, essentially. Let's go ahead and do it. If we take, I'm going to define delta to be the difference between the resonant frequency, which remember is the difference between the B and the A frequency for the system, and the electromagnetic field frequency. So we're going to call that delta. And I'm going to put delta in parentheses a lot of times so we don't think it's an operator that takes the difference between two values of a variable, but it's actually a value. So I'll take the derivative of the right-hand expression, CB. I'll get CB double dot, and let's see what I'm going to get. I'm going to get a CA dot, and I'm going to get a CA with a delta coming downstairs. And I'll solve the right equation for CA and plug back in to get something in terms of CB dot. I'll solve the left equation for CA dot. It's already solved for CA dot. I'll plug that in, and after a lot of algebra, which I'm not going to reproduce, you end up with this expression, which is a simple second order differential equation for CB. Notice it's you got a CB double dot, a CB dot, and a CB. This is screaming for a characteristic equation. If I assume CB has the form e to the lambda t, CB double dot, I get a lambda squared, CB dot, I get a lambda, and CB, I get nothing, I just get a 1. And I can produce a characteristic equation that looks something like this. It's just a quadratic that I can solve for lambda, and I get 2 roots for lambda. So we get these 2 roots, and the idea is to sort of factor things out. Notice that everything in the radical is negative, so that means it's going to be imaginary. We can factor that I out. I want to make a substitution. I want to define omega r, the Rabi frequency, to be what I get in the radical when I move the 2, the 1/2 in. In fact, multiply that through, and notice that it's the square root of the sum of the squares of the detuning, half of the detuning squared, plus half of VAB over h bar squared. And so the detuning and the size of the matrix element together determine the Rabi frequency. In the case when the detuning is 0, of course, you're just going to get the matrix element. But if I put all that in, I get a nice simple expression for lambda with the 2 different roots. I can put that back into my expression for CB. And notice that because there are 2 different roots, that means the general solution is going to be a superposition of e to the plus I omega RT and e to the minus I omega RT. But we also have to remember that the initial condition was that CB was 0, which means that A and B can't just be anything, but in fact B has to be negative A, because when you plug in t equals 0, the whole thing has to add up to nothing. And the only way you can do that is if b is equal to negative a. So I can rewrite the e to the plus I omega RT minus e to the minus I omega RT as a sine function, and get rid of the b since it's only minus a, and I get a simple expression which I can plug back in and figure out what CB dot is. Remember that CB dot was also related to CA, so I can use this to find CA. If I solve for CA, I get this hideous looking expression, but remember that at t equals 0, CA was supposed to be 1. So I can demand that when I put t equals 0 in here, CA is 1, and that tells me that all that junk has to be 1, which gives me an expression for A. So now I've got the boundary condition satisfied, or the initial condition satisfied, excuse me, that CA is 1, CB is 0, and that demands that A have a particular value. I can put that back in and finally have an expression for CA that's completely in terms of known things. And then that also determines CB, because once I have A, I can plug that back into the expression for CB, and I get general expressions for CA and CB as a function of time in terms of the detuning and the Rabi frequency. Now there's a special case I want to talk about, and that's when the detuning is equal to 0. If the detuning is equal to 0, then capital delta is 0, and the Rabi frequency reduces to VAB over 2h bar. If I plug that back in, I get a very simple result. I get that the A coefficient just looks like cosine, the B coefficient just looks like minus I times sine, and that means that the probability of being in the A state and the probability of being in the B state simply oscillate between 0 and 1 with a frequency equal to the Rabi frequency. Now I want to point out a couple of things. Both of these results, the first order perturbation theory result and the Rabi result, this so-called rotating wave approximation, are only valid if there are no other influences. So that means that, for example, no collisions, no other stuff going on. And in addition to that, they're only valid for a single well-defined frequency. And next time we'll generalize that a little bit. I'll even get into the field theory and how you can use field theory to treat the electromagnetic field not as a external classical electric field, but as an actual quantum mechanical beast in and of itself. All right, we'll see you guys next time.